We are going to talk about rate laws in 5.2. We initially learned last section that rates are a change in concentration over a change in time. When we look at chemical reactions, most are reversible. Often we only consider the forward reaction, where we have the reactants turning into the products. But you could reverse it where the products turn back into the reactants. And we're going to focus on those reverse reactions later when we talk about equilibrium more. But initially, the dominant reaction is the forward reaction because the only thing that we put in the vessel for the reaction to take place is the reactant. So the change in the concentration of the reactant depends on this. After a period of time, though, enough products will accumulate so that the reverse reaction becomes important. When the reverse reaction occurs, the change in the concentration of NO2 depends on the difference in the rates of the forward and the reverse reactions. So we can study conditions where the reverse reaction can be neglected, making the rate depend only on the concentration of the reactants. This is what we're going to do as we first study rate laws. This up here at the top is a rate law. Okay, so when I say find the rate law, just find the rate law, I want you to do that, where you actually write rate equals K is called the proportionality constant. It's temperature dependent. That just means for us that it might be under specific temperature, but if you change the temperature and have different data, then the K value could change. And then it's times the concentration of the reactants raised to N, which is called the order. Okay, so N is called the order. So if I say, what's the order of this reaction, and you know that N equals 2, you would say that it is second order. Okay, the order of the reactant could be an integer or a fraction. Usually it will be like 0, 1, or 2 when you solve for them. Both of these values, K and N, are determined by experiment only. So that means that for these problems, you're going to be given some experimental data. You're going to be given a data table full of information that then you will use to apply to the rate law. Some more important points: the concentrations of the products don't appear in the rate law because we are only focusing on the forward reaction, not the reverse reaction. And the value of the exponent N, the order, must be determined by experiment only. It can't be written from the balanced equation. A lot of times people think that the coefficient is the value for N, and it is not. It's a good guess, but if you have experimental data, then you need to solve for it from that. A rate law tells us exactly how the rate depends on the concentration of the reactant. So when we have the rate law, we can technically call it differential rate law, but we call it simply just rate law, and that's when it depends on the concentration. So we're going to see a lot of molarity values in these problems. A second type of rate law, the integrated rate law, expresses how the concentrations depend on time, and this helps us with graphing. We are going to focus on the integrated rate law in 5.3, but for now we're just going to do the regular rate laws for 5.2. Rate laws are usually dependent on the type of data that's easiest to collect, and knowing the rate law for a reaction is important, mainly because we can usually infer the individual steps involved in the reaction from the form of the rate law. So to determine the rate law, the first step is understanding how a given chemical reaction occurs. That means which reactant concentration must be raised in the rate law, and what is it going to be raised to. So we use the method of initial rates to do this. We did this in Chemistry 1, so this hopefully will just be review for you today. The initial rate of a reaction is called the instantaneous rate, determined just after the reaction begins, so just after time equals 0. And that could be like milliseconds, it could be minutes, it just depends on the experiment. Several experiments are performed, and then the data can be compared to see how the initial rate depends on the initial concentrations. And by comparing these, we can figure out the form of the rate law. So we saw our generic rate law before, right? Where rate is equal to the constant times the reactant's concentration raised to an n power. Okay? Well, Well, when we compare, what we're going to do is we're going to find a ratio. We're going to divide them. So if this is, for example, rate 2, then this is going to be the concentration of the second trial. So this is trial 2's rate and trial 2's concentration raised to the n power. Well, if we compared it to the same experiment's data, just or like a different trial of the same experiment, then I'm going to put rate 1 on the bottom. K is still the same. Then we have the concentration of A, and it's raised to the same power of n. It's raised to the same order. So mathematically what happens is the constants are gone. They cancel each other out. Okay? And if you're dividing two things that are raised to the same power, what we can do is we can simplify this. So this is going to turn into a ratio of rate 2 over rate 1 equal to, and this is a mathematical property and I don't remember the name of it, but we're going to divide the concentrations first and then know that they're raised to the same power as they were before. Okay, so the reason why we're going to need this equation right here is specifically for the value of n. Because you will have values, you'll have data to plug in for rates, you'll have data to plug in for concentrations, and you will just solve for what n is. You could do logarithms to figure this out, but usually it might be something as simple as 2 equals 2 raised to the n power, what's n? So you just have to kind of think about it, okay? So we're going to figure out initially, in example 1, when we have one reactant, how does this work? So we have A turning to B. The capital letters are the reactants and products. The lowercase letters are the coefficients. The coefficients don't matter. Okay, we need to write the rate law and determine the order of the reaction. So generically, the rate law is going to be rate equals constant times the concentration of the reactant. In this case, it's just plain old A raised to a power, and I'm just going to say X. So that means that the X values are coming from the A0 column. The A0 just means initial concentration. That was that 0 means, and then we have initial rate over here. So these are where we're going to plug in for rates, and this is where we're going to plug in for the brackets. Okay. Now, when we're comparing, like we just showed in that of how we're going to solve for this, we need to pick two experiments, 2 trials of information to plug in. It doesn't really matter when you just have one reactant, so let's just do 1 and 2. Now, I like to do the larger values in the numerator and the smaller values in the denominator because it's easier for me to figure out what the power is. So what that means, I'm going to do 1 and 2, and if you look, 2 has bigger numbers, so I'm going to take it as 2 over 1. Okay, so we have rate over rate, so 12 times 10 to the negative 4 over 3.0 times 10 to the negative 4 equals, then inside the parentheses, we will put the concentrations, and it's 2 over 1 again, so it's going to be 0.10 over 0.05. Okay, so now, and it's all raised to the x power, because that's what we're solving for. We're solving for that guy right there. Okay, so simplifying this out, the times 10 to the negative 4's go away, so 12 divided by 3 is 4 equals, and 0.10 divided by 0.05 is 2 to the x power. So now you can do your logarithm if you want to, but 2 raised to what power equals 4? That needs to be squared. So that means that x equals 2. Okay, in order to get the point for the rate law, what you have to do is, if you have a pencil, you could erase, or you could just write again, rate equals K times the concentration of A. But now, instead of plugging in x, we're going to plug in that x equals 2. So it's going to be squared. Okay? So this is half of our answer. This is the rate law. And then the other part of the answer, the order is the exponent. So that means if it's 2, that means that it is second order, because x equals 2. Okay? If it was a 1, it would be first order. If it was a 3, it would be third order. But since it's a 2, it is second order. Okay, so you might have to do those two things when you are solving your problems for this section. But what if you have more than one reactant? Well, when you have more than one reactant, every reactant's concentration will be raised to a separate power. They could be the same values, but we don't know that until we solve for them, okay? When each exponent in the rate law equals 1, the reaction is said to be first order in A and first order in B. Or you could have something called an overall order, which is when you add the exponents together, add the orders together. So if A and B were both 1s, then the overall order of the reaction is 2, or you could say that it is second order overall. Now, when you're doing these, I know you have a big blank space in your notes right now, and that's because the next example takes a lot of space. So if you need more workspace, back on page 6, you can do it. But what we're going to do, we're still going to use the rate over rate equals, and then have our parentheses for the concentrations raised to the power. But we want to make sure that we pick the columns that are constant in the area that we're not focusing on, okay? So we'll kind of see that, and if you need more help, you can ask me in person. But remember, don't assume that the coefficients are equal to the exponents. They're not always the same from the balanced equation. Okay, so we have a reaction between bromate ions and bromate ions in an acidic solution for this reaction. We have 3 reactants here. Use the data below to determine the orders for all 3 reactants, the overall reaction order, and the value of the rate constant. So we have 3 reactants, okay? We want to know the orders for all 3 reactants. We want to know the overall reaction order, and we want to know the value of the rate constant, K. Okay, so let's just write our generic rate law first. So rate is equal to K, our constant, times, and then this is where we throw in all of our reactants. So we have the bromate ion raised to a power, I'm just going to go X, times the concentration of the bromide ion raised to Y, times H plus raised to the Z. Okay, so we need to solve for X, Y, and Z. And just to help ourselves, I labeled X for this one, Y for this one, and Z for that one. Okay, so when we are comparing, the first thing we have to do is just find the orders, like we did in example 1, but we have to do it 3 times. Okay, so for X, if we're solving for X, we need to pick 2 experimental lines where the values in X change, but the values in Y and Z stay the same. So for X, that is experiments 1 and 2. Because if you look at the Y's, they're the same number, and if you look at the Z's, they're constant. They're the same number in both trials. So that means, just like how we kind of simplified before, when we were seeing how the equation works out, here, you notice how we got rid of the K? We can get rid of all of those other constant values too. If they weren't constant, we would have to include them. And it just makes life easier if we don't include them. Okay, so I'm going to show you how you could include them, but in the future, don't. So my next workspace is on this slide, so I gotta work here. Okay, so this is for the bromate concentration, which was X, okay? And we're doing 1 and 2, and 2 is bigger than 1, so I'm gonna have 2 over 1. So the rate of 2 is 1.6 times 10 to the negative 3 over rate of 1 is 8.0 times 10 to the negative 4 equals, and I'm going to write everything out and we're going to see how everything cancels, okay? So we have K over K, then we have 0.20, let's do it this way, over 0.10 raised to the x power. Then we have 0.1 over 0.1 raised to the y power. And then we have, again, 0.1 over 0.1 raised to the z power. Okay? So if you take something divided by itself, it equals 1. and 1 to any power is equal to 1. So that means that besides just the k's going away, we can also cancel out this part and we can cancel out that part. So in the future, we don't need to show that in our calculations because we already know that it will reduce, okay? So when you divide the left side of the equation, it is equal to 2, and then 0.2 divided by 0.1 is 2 to the x power, so x is equal to 1, okay? So that is our first order that we needed to solve for. If we go back, we're not done yet. We just know that, so for our rate law, this is my new one, rate equals k, and it's BRO3 negative. You can put a 1, or you don't have to. If it's not there, it's implied that it's not, that it's a 1. Okay, so now we're going to focus on the y. So we need to pick 2 rows where y changes, but x and z stay the same. And that is going to be 2 and 3. Because if you look at x and 2 and 3, they're the same value. And if you look at z and 2 and 3, they're the same value. Okay? And 3 is bigger than 2, so I'm going to put 3 in the numerator. So this is for the y, and that was on the bromide. And I'm going 3 over 2. Okay? So we have 3.2 times 10 to the negative 3 over 1.6 times 10 to the negative 3 equals, I'm going to simplify. I'm not going to I'm not going to do all that stuff that cancels out. I'm only going to do the stuff that's important. So we have 0.20 over 0.10 raised to the y power. Okay, simplifying that down, the left equals 2, the right equals 2 to the y power, so y is equal to 1. It just so happens that they're the same value for x and y. Going back here, then for my real rate law, I can going back to my real rate law, then I can just write BRM negative. If you wanted to add the 1, you could, but again, you don't have to. And let's do this again for that h plus, the z. Now, in our last 2 examples that we've done so far, they have been consecutive experiment lines. They don't have to be consecutive because in this case for z, the only ones that are constant in x and y are 1 and 4. So if you look at 1 and 4, they're the same, and 1 and 4, they're the same. Okay, so that is just an example of how it doesn't have to be consecutive. Okay, so for h plus, which I called z, we are doing, I'm going to put 4 over 1 because 4 is bigger. So we have 3.2 times 10 to the negative 3 over 8.0 times 10 to the negative 4 equals 0.2 over 0.1 raised to the z power. Okay, so then simplifying the left, that is equal to 4. Simplifying the right, it's 2 to the z power. Z is equal to 2, because 2 squared equals 4. So to finish out our rate law, we have h plus squared. Okay, so now we have determined the orders for all 3 of the reactants. Now we need to find the overall reaction order. So it's first order for the BRO3, it's first order for the BR minus 1, it's second order for the H plus, okay? To find the overall order, we just add those all up. So for the overall order, we would have 1 plus 1 plus 2 is a total of 4. So it is 4th order overall because we add up all of the exponents to get the overall order, okay? So that one's done. Last but not least, the value of the rate constant, k. So now that we know the orders and now that we know the rate law, we can just pick any experimental line of data that we want to and plug in and solve for k. And then that tells us what the constant k is. So I picked to use the experimental data from line 4, experimental 4, personally. Okay, so this order is coming from our rate law, where I have the rate. Oops. The rate is 3.2 times 10 to the negative third. This is for K when I'm solving for here. I know you're kind of crunched on space. Then we have 0.1 raised to the first power. Oops, sorry, I forgot my K. Plug K in there somewhere. And then we have 0.1 again, raised to the first power. And then we have 0.2 squared, because it's second order for the last one. Okay, so simplifying it down, you have K, and if I multiplied all those with squaring adequately, that was 4.0 times 10 to the negative 4. So K is equal to 8. Now for significant figures, you would need to say 8.0. There is a unit for K, but, and don't get scared by this, but it's liters cubed per moles cubed times seconds. The unit might not always be the same, so don't worry so much about the unit part. It's more about just solving for the order, so then you can solve for the value.